For years, the artificial intelligence race was a matter of sheer size, but we've crossed a threshold where carefully orchestrated networks of diverse AI models can outperform the largest individual systems on the planet. Training a single monolithic model is hitting steep physical limits. Squeezing out marginal improvements now requires massive data centers, thousands of specialized chips, and budgets stretching into the billions, all yielding diminishing returns. Beyond the computational cost, relying on one giant system introduces a structural flaw. Every model has specific blind spots and biases hardwired into it, dictated entirely by the unique data it was trained on and the human preferences used to align it. To solve complex problems, the strategy is shifting. Instead of exclusively building larger individual models, engineers are focusing on how to coordinate existing models at the exact moment a user asks a question. The most obvious way to coordinate AI is to spin up a group of agents and let them debate a problem until they reach an answer. It sounds elegant in theory. This diagram illustrates what actually happens in those unstructured debates. Researchers found that 29% of the time when an agent changes its answer, it isn't because the logic was superior. It folds because the other agents assert a position with high confidence. The loudest voice wins, dragging the rest of the group toward the wrong conclusion. Without a central mechanism to verify facts, a hallucination from a single node spreads unchecked. This independent structure amplifies errors by 17.2 times compared to a single model and triggers a cascade of retries that drives compute costs up by a factor of 10. To harness collective intelligence without the chaos, developers rely on a strict inference time architecture called mixture of agents. The data shows that simply increasing agent count without a rigid structural hierarchy often backfires. In these flat networks, coordination overhead grows so heavy that it negates the benefits of having multiple models in the first place. The mixture of agent system begins with a router. When a prompt arrives, this component reads the query, classifies its difficulty, and directs it to the appropriate tier of models, ensuring routine tasks don't waste expensive compute cycles. For complex queries, the prompt moves into the proposer layer. Here, the exact same question is sent simultaneously to a horizontal array of independent models to generate isolated baseline drafts. Using identical copies of the same model wastes resources, yielding nearly identical logic. To work, proposers must come from different sources, like Meta, Google, or Mistral. Distinct training and algorithms mean they catch different edge cases, approaching problems from entirely different angles. Because these models never see each other's work during this phase, their genuine diversity creates a much broader, more resilient pool of raw reasoning than any single system could produce. Those independent drafts are then forwarded to the architecture's central immune system, the aggregator model. This is the single node responsible for final synthesis. It evaluates the entire set of auxiliary drafts at once to cross-check logic, filter out hallucinations, and isolate the strongest arguments from the group without falling victim to conformity bias. Comparing context loss, independent networks rapidly lose track of information, but a centralized aggregator reduces context loss by exactly 66%. By analyzing where proposers agree and disagree, it strips away errors, weaving isolated correct elements into a single, unified final answer. Collective intelligence depends on this rigorous, centralized synthesis. It's what allows the system to take a collection of flawed inputs and refine them into a high-quality conclusion. Looking at this line graph tracking benchmark win rates, we see a specific result. A 6-proposer setup built entirely from smaller open-source models consistently outperforms a single top-tier proprietary baseline model. But this system is bounded by capability saturation. If a single model can achieve a success rate over 45% on a basic task, adding a network of agents provides zero additional performance benefit. Deploying this matrix for routine coding edits or simple formatting creates a steep coordination tax. You consume substantially more compute resources and increase system latency without improving the actual answer. Single models remain the most efficient tool for standard tasks. But when a problem reaches the edge of a model's capability, these structured collaborations allow us to extract deeper reasoning from systems we already have.